If we change the pressure, how does that affect the equilibrium? Pressure is going to only change the equilibrium or shift the equilibrium concentrations if the products and reactants have at least one gaseous species, and if the number of moles of the gaseous reactants does not equal the number of moles of the gaseous products. Right? So what this is saying is that we need some imbalance of moles of gas for pressure to stress the system. Right, so on our product side and our reactant side, we need to have a different number of moles of gas. And this will ultimately be related to the concentrations of those gaseous products and reactants. And remember, when we're looking at equilibrium, gaseous products and reactants are the most dominant in determining the equilibrium. And so the ways that we change the pressure of the system is by increasing or decreasing volume, right? If we look at our ideal gas law, P equals nRT over V, pressure and volume are inversely proportional. So if we decrease the volume, that means we increase the pressure. And if we do the same thing, or the inverse, if we increase the volume, then we're going to decrease the pressure. Right? If we're dividing by a smaller number, this whole ratio gets larger, so the pressure increases. If we're dividing by a larger number, this whole thing gets smaller, so the pressure should decrease. Right? So we're just thinking about analyzing for constant number of moles, constant number of R is constant, and for the same temperature, right? We're not changing the temperature. And that's why we have to say at constant temperature for each of these, because temperature will end up shifting the equilibrium as well. Right? And the reason that we're kind of thinking about it in terms of volume is because this change in pressure is related to the change in volume. And if the number of moles, right, is involved here, this is like the concentration, right? N over V is like the concentration times RT. Because increasing the pressure, isn't necessarily intuitive how that changes the equilibrium, but if we think about changing the volume and therefore the concentration, that'll make a little bit more sense in what we've talked about in terms of how the concentration adding a reactant moves the reaction in a different way. Right? So to predict the equilibrium shift, the effect of increasing the pressure or decreasing the volume is the effect of increasing the concentration of the gaseous reacting species. Right? If we decrease P, that's like the same thing as, if we increase P.
Wait, so if you're to increase the pressure, that would make the concentration higher because the volume is smaller?
Yep, that's exactly right. Because as you increase the pressure, that's equivalent to decreasing, I'll write that a little neater, the volume. Right? And if the concentration is related to N over V, if we decrease the volume, what happens to the concentration? It increases, right? Because the concentration is inversely proportional to the volume. So if we decrease V, that's like increasing the concentration of whatever that species is, right? So I'll put that over here. N over V. If this goes down, then the concentration is like going up. So that's why these two things are equivalent to each other.
So pressure in this situation is technically proportional to
The concentration?
concentration?
Yeah, and we have an idea of that, right? Because we can write the equilibrium constant in terms of just the pressures of the gas, right? It's modified by that, remember that 1 over RT delta N. It's modified by that, but we can express equilibrium in terms of the pressures, right? And it's also because the ideal gas law relates this thing right here as a concentration to the pressure for gases. And again, this has to do with the fact that they're ideal gases, they don't interact and stuff with each other either. Lee, did you have a question?
So if we increase the pressure,
So this is one that I feel it takes some kind of thinking to wrap your head around why this happens. Right? If we increase the pressure, maybe if I go to the next slide, that'll help a little bit, right? Clear things up. If we increase the pressure, right, it's like we're pushing down on the piston, right? You feel more and more resistance, which is the pressure that's being exerted back on you, right? You increase the pressure, and we notice the volume is decreasing, right? So now the effective concentration of all the gaseous molecules has gone up. Remember, the other condition is that we need to have an imbalance of moles of gas on the product side and the reactant side of the reaction. So if the effective concentration has gone up by changing the volume, but there's the same number of moles of gas on each side, then effectively you change the concentration equally on both sides of the reaction. Right? Let's say we had, see if I can draw a picture that represents this. We have this volume, and we have 1, 2, 1, 2, 1, 2, and our reaction is like A plus B goes to C, right? So and I should actually change this. It'll be A plus B goes to 2C, right? And we have the same number of moles of gas on each side of the reaction. Assume everything is a gas here. If we increase the pressure, all right, all we've done is change the volume. The concentration of each of the gas molecules on the reactant side and the product side has changed proportionally the same amount, right? Which means that all we've done is change the volume, but the relative concentrations, the ratio of them, hasn't changed at all, right? But if we have a different number of moles of gas on the product or the reactant side, so let's say we do something like this down here, and now we have duplicate. Let's say we have 3 A molecules. Now that there's an imbalance of reactant molecules, we've effectively increased the concentration by the reactants more than we have for the products here. Right? Because it's proportional to the pressure, which is proportional to the concentration and the volume with the number of moles. So if there's more moles, the concentration changes more. Right? If we have the ideal gas law, if the number of moles is different, then the pressure changes proportionally to the number of moles. Right? So if we have 4 moles on the reactant side and only 2 moles on the product side, and we change the volume, the pressure is changing twice as much for the reactants as it is for the products. Which means that we're effectively increasing the concentration of the reactants twice as much as the products. And so if we do that, we're going to shift to the side that corresponds to adding the concentration of more moles of gas. Or the side with more moles of gas, if we increase the pressure, which is decreasing the volume, we're going to shift to the side with less moles of gas. So it shifts in the direction of less moles of gas. So you think about it, we want to make that ratio of pressures the same for products and reactants, right? That's our equilibrium value. So when we increase the pressure, we need to shift to less moles because effectively we're increasing the side with more moles of gas, the concentration of that more. So it's like an effective increase in concentration of the side with more moles of gas. And vice versa, if we reduce the pressure, we're going to shift to the side with more moles of gas. Right, so by changing the pressure, if we're increasing it, we're increasing the concentration of the side with more moles of gas, more than the reactants. Or not the reactants, than the side with less moles of gas. So we shift the equilibrium, or we shift the reaction to counteract that change. Right, so here we have 4 moles of gas. Here we have 2 moles of gas. We increase the pressure. Concentration of these is increasing more than the concentration of the products. So we shift to the right for this reaction. In this case, we decrease the pressure. Right, now we're effectively decreasing the concentration. So it's like we're taking a reactant away because we have more moles of gas. So we're decreasing this concentration more than we're decreasing the product, right? So that creates an imbalance. We need to move towards the reactants in this case to counteract that change. Right? We don't have to go into the whole philosophy or, thinking about it that deeply. We can just remember that if we increase the pressure, it's gonna shift towards less moles of gas. If we decrease the pressure, it's gonna shift towards more moles of gas. But the reason for that is because when we change the volume of the system, the side with more moles of gas is changed more than the side with less moles of gas. So that creates an imbalance and the reaction has to move to counteract that. All right, any questions on that? I know it's...
So if it's balanced,
Mm-hmm.
then there's no changes because it's a balanced number of moles.
Yeah, exactly. If it's equal number of moles on both sides, right? So like this,
Like that first one.
yeah, like this one right here, there's equal number of moles of reactants, right? These green and blue are reactants. Then as we change the concentration, or as we change the pressure and the volume, the concentration is changing proportionally, right? Which means that as we change the concentration, we're maintaining that, or not the concentration, as we're changing the pressure, we're maintaining that equilibrium ratio as we increase, we expand and compress the piston. So it doesn't shift the reaction in either direction. It's only when we have this imbalance of moles that changing the pressure changes the concentration of the reactants versus the products differently. Right, so you have to compensate. The reaction actually has to change or move to compensate for that change in volume or change in pressure or change in concentration, right? Those are all intimately related for gases because of the ideal gas law. Did that answer your question? No. Right, you can think if we have equal number of moles, when we expand or compress the piston in that chamber, everything changes together. And it changes following that equilibrium ratio. But when you have an imbalance of moles of gas, that change in pressure affects more moles of gas more, right? And we can see that just by looking at the ideal gas law, right? If this one, we have 3 times the moles of gas versus here we have 2 times the moles of gas, 2 nRT, right? If we include this as the concentration, we see that change in pressure affects the concentration more for the one with more moles of gas. Right, those colors aren't related to any of these colors here, but they're just two different cases, right? This pressure, right, changing this pressure is gonna affect the concentration less than changing this pressure because we have three N whatever moles of gas, and this one we only have 2. Alright, so this is how pressure affects the equilibrium. So if we had this reaction here, and we increase the pressure or decrease the pressure, which direction will the reaction move? Which direction is it going to move if we increase the pressure?
Towards the reactants.
If we increase the pressure, that's like decreasing
Oh,
the
the
concentration,
clockwise.
right? So that means that
Otherwise-
this concentration is going to go up. So it's going to move towards less moles of gas, right? So the first thing you want to identify if we're looking at a gaseous reactant is which side has more or less moles, right? So how many moles of gas are here?
2,
2, and here
4.
4, right? So this is the exact example that was in the piston, right? So 2 and 4. So this has less moles, and this has more moles, right? So increasing the pressure is like decreasing the volume, which is increasing the concentration. We're increasing the concentration of this side more, so we shift it right to compensate. And what about decreasing the pressure?
That will go towards the reactant.
Yep, that'll move towards the reactants, right? Because this side, we're decreasing P, we're then decreasing the concentration. This concentration gets changed 2 times less than that concentration. So we're gonna shift towards, this one is decreasing at a rate that's 2 times more. And so that was, the next slide is exactly what I just wrote there, so I'm gonna skip the table there. What about for this reaction? Do the same thing, we'll increase P,
There's no change, right?
P, and then decrease P. So give you guys just a second to think. All right, so the first thing you want to do is identify number of moles of gas on each side. So how many moles of gas are on the left side? Right, so one thing we always keep track of whenever we're looking at equilibrium is what? The states of matter, right? So we always have to keep track of that. Why? Because solids aren't included, and especially if we have gases, gases dominate the equilibrium, right? So because the solid is there, we don't include it in our equilibrium, and then when we're considering shifting a reaction, we only think about the gases here, right? So there's gonna, how many moles on the reactant side? 1 mole, right? And on the product side, 2 moles, right? Because this is also a gas. So we have 2 moles of gas here, 1 mole of gas there. So if we increase the pressure, which direction is the reaction going to shift? I'm going to point with your left or right. Yeah, it should shift this way, right? Because we're going to shift towards less moles of gas. All right, so unlike just increasing or decreasing concentration, we don't just look at, is it on the reactant side or the product side? We're actually looking at how many moles of gas are on each side of the reaction, right? So it's a little different than just looking at concentrations, because it doesn't depend on, just increasing the concentration of this. It depends on the number of moles of gas, right? So the concentration is a little easier. You just say, okay, I'm adding here, that's moving the opposite direction. I'm removing here, I'm moving in that direction. Here we have to think about the moles first. What about decreasing the pressure? Then that'll go the opposite direction, right? Because we're going to be moving towards more moles of gas. Why? Because effectively decreasing the pressure, we're decreasing the concentration of this 2 times as much as we're decreasing this concentration. As that happens, as we progress, this means you're going to be changing this concentration a lot faster. The reaction has to move to account for that change from equilibrium. All right, so again, the little table is the same thing as what we're writing right here, so I'm just going to skip over that. All right, any questions on pressure or how pressure affects equilibrium? Question? All right, So the last thing we're going to talk about for our first chapter on equilibrium is how then the temperature changes the equilibrium. So just like pressure and concentration, the system will respond to counteract whatever change it is that shifts the equilibrium, right? If we add something to the system, the equilibrium will move, or the reaction will move to counteract that change, right? So if we have a change in temperature that, right, so let's say the temperature is increased, the reaction will shift in a direction that does what to the temperature, do you think?
Decrease would be?
Yep, it should decrease the temperature, right? So if we increase the temperature, the reaction will shift in a way that decreases the temperature. If we decrease the temperature, the reaction will shift in a way that increases the temperature, right? So that sounds a little counterintuitive, right? Or not necessarily counterintuitive, but just sounds a little funny, right? Like, how does a reaction shift towards changing the temperature? So does anyone have any idea what this might be related to for the reaction, Colin?
Endothermic or exothermic.
Yeah, so all our reactions, unless they're isothermic, will either release or absorb energy, right? So if you guys remember, Q equals ms delta T, right? If we absorb or release energy, that results in a change in temperature of the system, right? As we absorb energy, we're taking kinetic energy from all the molecules, which changes the temperature of the system. And so it depends on if the reaction is endothermic or exothermic or endothermic. So if we have an exothermic reaction, right, if I have some products here or some reactants, this is our energy, right? Where are the products going to end up for this reaction, right? This is a little potential energy curve, right? This little curve of the energy as the reaction proceeds.
It's gonna go below.
It should be below, right? Remember these curves. The products will be down here, and then this difference right here is the change in enthalpy, right? That change in enthalpy is negative for an exothermic reaction. All that means is that we end up below the energy of our reactants. For an endothermic reaction, where does it end up? Above, right? So now we see this is our delta H, our enthalpy. Our enthalpy is going to have a positive value because we end up higher than where we started. Right? Whenever we have a delta, just to review, that just means what? Right? How would you write this out mathematically? The final minus the initial, right? So that's how we determine if it's positive or negative, right? If we end up, if this value is larger than that one, this whole thing is positive. Here, the final is less than the initial, so when you subtract something smaller by something larger, you get a negative value, right? That's how we determine the sign of these. And so if we have an endothermic reaction, these will be relatively simple actually. We don't have to think about moles of gas and get all confused. How's this related to ideal gas law and stuff? We can just think of the heat as a product, right? If we change the temperature or we add heat to the system, or for an exothermic reaction, it's like one of the byproducts of the reaction is temperature change or energy, right? As the reaction happens, right, every time the reaction happens, we release a certain amount of energy to the surroundings, right? And then if it's an endothermic reaction, how do you think that we treat that?
It's a reactant.
It's a reactant, right? We take in energy from the surroundings for the reaction to proceed. So the heat is going to be a reactant. So this is going to be a product, and this is going to be a reactant. And so this is obviously just kind of figuratively a way that we can represent this, but it makes it easier to analyze then how does change in temperature affect the equilibrium, right? Because if we think of it as a product or reactant, then increasing or decreasing the temperature, right, is just like increasing or decreasing a product or a reactant. So there's going to be 4 different scenarios that you end up looking at. So if we have constant pressure and then raising the temperature of an endothermic reaction is thought of adding heat to something on the product side, right? So think of heat as a product, and if we increase the concentration of the product, which direction should the reaction shift?
Towards the reactant.
It should shift towards the reactants, right? If we're adding this, it's like the same thing as we're adding NH3 here. Why? Because it's a product, so the reaction is going to shift in that direction. Shifts the reaction to the reactants. If we conversely lower the temperature, that's like removing our product of heat, right? We remove this, the reaction shifts to compensate, and so this is like taking temperature away. The reaction is going to shift to increase the temperature of the system. We do that by causing an exothermic reaction to happen, right? As the reaction happens, it releases heat. So we shift to the products in this case. And that just means if we have an endothermic reaction, it'll have the opposite trend for an exothermic reaction, right? If we have an endothermic reaction, heat is treated as a reactant because we take in energy from the surroundings to cause the reaction to happen. So if we add heat, right, we're adding temperature to the system. The way we reduce the temperature in an endothermic reaction is by the reaction proceeding, right? Because it's taking temperature, it's taking energy from its surrounding to make the products here, right? So if the temperature of an endothermic reaction is increasing, the reaction shifts to the products to absorb the heat, right? It wants to counteract that change to the system. We're adding temperature to counteract that change. It's like the energy we're putting in shifts the reaction to the right. And so this is what you're doing when you're stirring a solution, right? You're stirring it, you're adding energy to the system. The endothermic reaction takes that extra energy and causes it to create the products wherever it is that you're looking at. On the other hand, if we're removing it, right, so we're removing heat, we're lowering the temperature, an endothermic reaction to increase the temperature of the system will shift in the opposite direction, right? So if we look at our energy curves for this, right, an endothermic, sorry, this should be endothermic, something like that. This will be NO2 here into O2, right? We end up at higher energy, so we're taking that extra energy to make the products. When we're going in the reverse direction, it's like flipping this the other way, right? We're starting from NO2 and we're making N2O2, right? So the reaction in the reverse direction is an exothermic reaction. So that's going to shift towards the reactants. Qualitatively, as the heat changes or the temperature changes, if it's endothermic or exothermic, we just treat those as a reactant or a product, and like we're changing the concentration of that reactant or product. This should be energy. Right, so just to summarize, increase in the temperature causes the reaction to shift left for an endothermic reaction. Right, decrease in the equilibrium constant, and decrease in the temperature causes the reaction to shift right, increasing the equilibrium constant. And when we talk more about thermodynamics, after our discussion on equilibrium, we find that this temperature is also related to the equilibrium constant itself, in the difference in not energy, but the free energy of the system. And then in an endothermic reaction, heat is a reactant. Increasing it is like increasing the concentration of reactant. We shift to the right, increasing the equilibrium constant. In decreasing the temperature, we shift towards the decreasing concentration species, which is the reactant of heat here. So we shift towards the left. All right, so here we have an example for the formation of these. and we're given a value for the enthalpy of this reaction, right? So why don't you guys take a second and see how that changes the equilibrium. So this is basically going to be an arrow left or right, this is an arrow up or down, and then this is how the equilibrium constant changes. What kind of reaction is this?
Exothermic.
Exothermic, right? Because the negative sign here, that means it's exothermic, so we treat the heat or temperature change as what?
Is a react
Product, right? We treat this as a product, right? So if we increase the temperature, that's like increasing the concentration of a product, what happens to the equilibrium? It should shift to the left, right? We increase this, the reaction is going to shift to counteract that change, right? So we increase to the left. This is going to decrease the temperature of the system. If we look at the amount of the reacting species, right, N2H2 and NH3, what happens to those? What happens to nitrogen?
goes up.
It increases. What about hydrogen? It also goes up. And what about ammonia? It decreases. Right, so how will that change our equilibrium constant?
It would decrease it because the reactants.
Right, our equilibrium constant is NH3 over H2 cubed and 2. Right, that's our equilibrium constant. If we increase both of our reactants and decrease the numerator, then our equilibrium constant should decrease. And what about decreasing the temperature? How will that change? Or which direction is the equilibrium going to shift or the reaction going to shift? It should shift right, right? Because if we're decreasing this, the equilibrium moves to increase the concentration of this side of the reaction. It moves to then increase the temperature of the system because we're decreasing the temperature. Temperature increases because as the reaction goes forward, right, we release energy, which increases the temperature of the system. So then that should shift to the right. So then what happens to our reactant species here? They go down, right, for both of them. And then the product should increase. And what happens to our equilibrium constant? It increases, right, because we have smaller numbers in the denominator and a larger number in the numerator, right? So this should increase. And so this is the first time we're looking at how does the equilibrium constant depend on something, right? We see just from analyzing from Le Chatelier's principle without doing anything with thermodynamics that if we change the temperature of the system's response to counteract that change or that stress to the system will give us a new equilibrium here. And so this is actually a new ratio that's being made here, right? Because it's this quantity right here depends on the temperature, right? So as we change the temperature, this ratio should change. And how does it change? Well, it depends if it's an exothermic or an endothermic reaction. All we can do this is qualitatively now, how does it affect? We'll talk about the explicit dependence in the future, right? So it'll be something like the Arrhenius equation, but for an equilibrium system rather than an out of equilibrium system. All right, are there any questions on that? All right, how do we feel about Le Chatelier's principle? Thumbs up, thumbs to the side, thumbs down. Okay. All right, so we'll get some more practice with that. So these are good kind of qualitative type questions, right? Good multiple choice questions, right? It's easy to say, okay, increase the temperature, which direction does the reaction shift, and what happens to the concentration of the products? And it's easy to permeate, 4 different answers to a question like that, right? So, and it's also a good way to kind of get a feeling for ice tables, right? How should equilibrium move? How should the equilibrium constant change just by changing something in the system, right? So if you're doing an ice table, right, and you add some of this to your system, that changes the equilibrium, you do an ice table, well, your solution, right, whatever you find the change should be, you should increase the concentration of your products in that case. All right, let's take like a 12-minute break, and we'll come back and we'll start solubility.